Welcome to my video, The Nature of Time. I would like to present my hypothesis regarding the nature or essence of time, which is based on the special theory of relativity and adds an additional dimension of the four-dimensional space-time commonly used in that theory. This also includes, among other things, an explanation of the nature of matter. As the subtitle indicates, relativistic dynamics and five-dimensional space are described, and the energy of four- and five-dimensional velocities is specified. A video cannot explain things as thoroughly as a written article. You can find the articles underlying this video with detailed justifications, formulas, and proofs on my website listed here. To give you an impression of my hypothesis right from the start, I will now reveal the key point, my definition of time, up front, even though it is likely hardly understandable at this point. Time is the variable spatial coordinate of the four-dimensional cross-section of a five-dimensional Euclidean space, which consists of the three-dimensional universe plus a fourth spatial dimension, and shifts at the speed of light perpendicular to all four directions of propagation in the fifth dimension.
The idea of an additional dimension that can only be experienced indirectly likely originates from Plato's allegory of the cave. There, however, it refers to an ideal realm of ideas in which the laws of physics do not apply, whereas here they are supposed to do. The prisoners sitting behind the wall see only the two-dimensional shadows of the three-dimensional figures. In the camera obscura, too, reality is seen as a projection. In 1921, Theodor Kaluza, a private lecturer in Königsberg, introduced a fifth dimension to unify gravity and electromagnetism, but this did not gain recognition. In 2025, on the occasion of the spring meeting of the German Physical Society, I visited his grave at the Göttingen City Cemetery. Meanwhile, however, theoretical physics works with four-dimensional velocity and momentum vectors. See the English Wikipedia article Mass and Special Relativity.
For dynamics, we need three formulas from kinematics. So let's start with a bit of four-dimensional kinematics, introducing four-dimensional velocities in the fourth spatial dimension. Time is then the fifth dimension.
Using this equation from special relativity, we calculate the time t dash in the rest frame of a body and event from the time t in an observer's reference frame. The event here is that a rod of length L equals 3 light seconds is moving in the positive x direction at a velocity Vx equals 0.6 c. You can see the world line of its tip. It has just completely passed the origin and is represented by the purple line on the x-axis. If you square the equation, the square root cancels out. Then you expand the parentheses and Vx times t is exactly its length L. This yields the Pythagorean theorem, to which the right-angled triangle with sides t dash, blue dashed line, L and t, the green circle radius, belongs. L by c and L have the same magnitude, because L is measured in light seconds and 1 light second is equal to c times 1 second. That is, the c cancels out. But why does the dashed hypotenuse have the length t dash?
When the tip of the rod passes the origin, a flash of light is triggered there. Its spherical wavefront is shown after 5 seconds. The light green rectangle around the t-axis represents a light clock. This is an evacuated tube with mirrored ends, between which the light wave, or rather its photons, are reflected back and forth. A photon takes 5 seconds to travel this distance. It could also be nanoseconds and nanolight seconds, in which case the tube would only need to be 1.5 meter long. For simplicity, seconds and light seconds are shown here. If the light clock now moves along with the tip of the rod, let's consider a photon of the spherical light wave that has just the right direction to always remain inside the tube. It arrives at point B after 5 seconds in the observer's frame of reference. In the moving light clock, in the rod's rest frame, however, less time has elapsed. Here it is exactly 4 seconds. To the observer, this time appears to be increased, stretched, or dilated to 5 seconds.
This equation represents length contraction, since the square root factor is always less than or equal to 1. Here, too, we square the expression and expand the parentheses. The x by c times L dash is a distance, which we call S here. Once again, we obtain the Pythagorean theorem. This involves the right-angled triangle with sides L, now plotted on the t-axis, the upper yellow segment S, and the red segment L dash. The leg L is, of course, shorter than the hypotenuse L dash. That is, for the observer, the rod length is contracted. Thus, L dash and T dash can be determined in this way by construction without calculation. It is curious, however, that the length L runs in the time direction and that L dash also has a time component. And the physical significance of the segment S remains entirely unclear. In such an elementary equation in which L and L dash have physical meanings, S must also have one. Now the concept of a fourth spatial dimension comes into play. To remove the time components from L and L dash, reflect the triangle OCD with sides L, L dash, and S across the dashed angle bisector. Then rotate it another 90 degrees around the x-axis in the W direction of a fourth spatial dimension. Now L and L dash are purely spatial quantities, and S has the physical meaning of the distance component traveled in the W direction. That is, in this conceptual model, the rod actually moves at an angle psi to the x-axis, and L and S are the two components or projections of this motion. From this follows the first equation. In the W direction, the tip of the rod in the observer's frame travels a distance s in time t. Therefore, the second equation applies to its velocity component Vw. Here, s is replaced by v by c times L dash, and then L dash is replaced by L times gamma. Finally, L by t is replaced by Vx, resulting in Vx squared. In this representation, the time axis is omitted and the xy plane is placed in the plane of the drawing layer. In the observer's frame of reference, Vx is equal to L by t and V is equal to L dash by t. It follows that the velocities are in the same ratio to each other as the distances or rod lengths. The distances and the velocities thus form similar triangles in the diagram. According to equation 1, L by L dash equals 1 by gamma, and thus Vx by V also equals 1 by gamma. Therefore, equation 3 holds. V equals gamma times Vx.
The kinematics discussed so far were necessary as prerequisite for dynamics. They are presented in greater detail in the article Rest Length and Rest Time in Five-Dimensional Spacetime at www.roland-sprenger.de. Now we can finally turn to the legitimate question of why we have not yet noticed anything about four-dimensional velocities, such as their energies. Let's start with momentum, which is also a conserved quantity independent of the reference frame in the theory of special relativity. A body with relativistic velocity Vx in the x direction and total mass m has momentum p equals m times Vx. Traditionally, a relativistic mass increase is assumed, and m is calculated as rest mass m null multiplied by gamma. However, if one factors out the last two terms in this product, the term inside the parentheses is precisely the four-dimensional velocity v, and the relativistic momentum is now the product of the rest mass and the four-dimensional velocity. This would imply that the rest mass is conserved, but the velocity is greater by a factor of gamma than the measured three-dimensional velocity. This can be explained by the hypothesis presented here regarding four-dimensional velocity. Modern theoretical physics does indeed assume that mass remains constant, even at relativistic velocities. So one does indeed perceive something of the energy of the four-dimensional velocities, and consequently of the velocities themselves. The relativistic mass increase was an interpretation of the measurement results for momentum and three-dimensional velocity. For the equation P equals m times v to hold, either m or v had to be larger. Of course, people were reluctant to introduce a fourth spatial dimension since it cannot be directly perceived. But the idea that mass increases with velocity is also strange.
Now we turn to the energy momentum invariant E squared minus in parentheses Cp squared equals E null squared. This too can be easily derived using four velocity. The famous formula E equals mc squared can be applied further if interpreted correctly. From E equals mc squared equals m null gamma c squared and E null equals m null c squared, it follows that E by E null equals gamma. And from equation 3 it follows that V by Vx equals gamma. From both equations it follows that E by E null equals V by Vx. That is, the energies are in the same ratio to each other as the velocities, and therefore form similar triangles in the diagram. What now is the length of the third side of the energy triangle? In the blue triangle of velocities in the diagram, we have v squared minus vw squared equals vx squared. From equation 3, v equals gamma vx is substituted, and from equation 2, vw equals gamma by c times vx squared. Both sides are multiplied by c to the power of 4 by vx squared. Then the equation is multiplied by m null squared. Next, all factors of the summons are squared together. The first parenthesis then contains the total energy E. The second parenthesis contains the four-dimensional momentum m null v with gamma Vx equals v. And the third parenthesis contains the rest energy E null. Thus, the energy momentum invariance is derived much more simply from the four-dimensional velocities v and vw without the usual integration. This is further evidence for the existence of four-dimensional velocities. In the three-dimensional interpretation of this invariance, the momentum is p equals mvx equals in parentheses m null gamma times Vx. In this four-dimensional interpretation, P equals m null V equals m null in parentheses gamma Vx. which is equivalent since we are dealing only with magnitudes. The short side of the red energy triangle thus has a length equal to the magnitude of Cp, that is without units, where p is the momentum of the four-dimensional velocity v. If one expands equation 6 for E, substituting the magnitude of the four-dimensional momentum, one obtains equation 7. It represents the total energy as a function of the four-dimensional velocity. The segment marked with a curly bracket in the upper section of the hypotenuse corresponds to the total energy Ek equals E minus E null. It follows from equation 1 that as Vx increases, the angle psi also increases. In this process, the distance corresponding to Ek approaches infinity, just as is consistent with a relativistic mass increase. Now the chapter Force and Acceleration. In linear accelerators, an accelerating electric force acts on the charged particles, in this case in the x direction, which increases their momentum. The following applies, because gamma contains Vx. As an intermediate calculation, first take the derivative d gamma to dt using double differentiation. The result is inserted. And if we factor out m null gamma ax and square the squares together, we obtain equation 8. Solving for ax yields equation 9.
We will need this term again in a moment, but first let's discuss it. As Vx approaches 0, gamma approaches 1. And Vx times gamma by c approaches 0, meaning that only m null remains in the denominator. In the limit, we then have ax equals f by m null, that is Newton's second law. And when Vx approaches c, gamma approaches infinity. And thus the entire denominator, the value of the fraction, and the acceleration all approach 0. This is the case for linear accelerators several kilometers in length. However, the force that continues to act imparts additional energy to the particle, which now leads only to the acceleration of Vw and thus to an increase in psi. The particle therefore describes a curve with left-hand curvature in the xw plane. Only its three-dimensional projection is located in the linear accelerator.
The diagram shows the four-dimensional velocity vectors v for an accelerated particle at the three-dimensional velocities Vx equals 0.5 c, 0.8 c, 0.9 c, and 0.99 c. In equation 2, gamma is substituted and the expression is simplified slightly. Equation 10 describes the graph in the figure on which the tips of the velocity vectors lie. As Vx approaches c, the denominator approaches 0 and Vw approaches infinity. In four-dimensional space, the following applies to acceleration. Vector A equals vector delta v over delta t. In three-dimensional space, the following applies. Vector ax equals vector delta vx over delta t. From this follow the next two equations. In the figure, delta v is the blue vector arrow and delta vx is marked on the horizontal axis. Parallel to the vector delta v lies the red four-dimensional acceleration vector a, and below it is its ochre-colored three-dimensional component ax. As delta t approaches 0 and thus also delta v approaches 0, the second vector A becomes a tangent vector, and delta v over delta vx becomes the derivative dv with respect to dvx. So A equals ax times the derivative dv with respect to dvx, where v equals gamma vx. The formula is derived. Then another intermediate calculation for the derivative d gamma with respect to dvx. The result is substituted in and gamma is factored out. Again, the terms are squared together and gamma vx is replaced by v. Now the term for ax from equation 9 is substituted in and then reduced.
The result is Newton's second law. In four-dimensional space, Newton's second law therefore also holds for relativistic velocities. This too is a well-known result in theoretical physics, which in turn confirms the approach used here. It appears to contradict the last figure, since there, with constant delta Vx increments, longer and longer delta V arrows appear as Vx approaches C, so that delta Vw and thus A by no means appears constant. However, the times delta t must be taken into account, which increase accordingly as Vx approaches C. Equation 11 must also hold vectorially, that is, in four-dimensional space, this hypothesis posits the existence of an accelerating force whose direction is that of the respective tangent to the drawn curve.
The m null squared c squared under the root is factored out, and the square root is partially taken. The new root then represents a velocity, denoted here as ve. M null times ve is a momentum, denoted by pe. This is now interpreted to mean that a particle with total energy E and mass m null has momentum pe equals m null times root of, in parentheses, c squared plus v squared, and moves with velocity ve equals root of, in parentheses, c squared plus v squared. The corresponding velocity vector ve is therefore the hypotenuse in a right-angled triangle with the velocity vectors c and v. The vector v lies in the xyz plane. The vector c must be perpendicular to it. In five-dimensional spacetime, this leaves only the time direction. In the figure, the velocity triangle is shown in black. The corresponding energies are represented as red lines, with a proportionality factor magnitude of m null c equals 1. The blue lines are world lines. The velocity vector ve is five-dimensional.
A particle with total energy E therefore has a five-dimensional velocity ve and moves in the direction of time at the speed of light. A particle at rest possesses only the kinetic energy associated with this motion at the speed of light. This energy, formerly called rest mass, with the proportionality factor c squared, is also inherent in moving particles. It remains constant in this respect and is now simply called mass. The former dynamic mass is the kinetic energy of the five-dimensional velocity. Since the totality of all particles constitutes the universe, one can say that the universe moves at the speed of light in the direction of time. Now the definition of time mentioned at the beginning becomes clear. Time is the variable spatial coordinate of the four-dimensional cross-section of a five-dimensional Euclidean space, which consists of the three-dimensional universe plus a fourth spatial dimension and shifts at the speed of light perpendicular to all four directions of propagation in the fifth dimension.
The presumed reality of four- and five-dimensional velocities, and thus of a fifth dimension, is therefore reflected in the alleged relativistic mass increase. This will now be calculated from the four- and five-dimensional velocities and illustrated. The kinetic energy of a body moving relativistically is given by this sequence of terms. This is solved for delta m. It follows delta m equals m null by c times, in parentheses, Ve minus c. The so-called mass increase thus depends linearly on the five-dimensional velocity magnitude of Ve and is directly proportional to the difference in the magnitudes of the velocities Ve minus c. The latter is marked with a curly brace in the figure. This dependence is much simpler and more intuitive than the dependence on the three-dimensional velocity Vx.
I will now move on to the summary and outlook. The article Relativistic Dynamics and Energy in R5 at www.roland-sprenger.de provides additional statements and illustrations regarding energy in four- and five-dimensional space. The hypothesis, which is presented there in somewhat greater detail, is based on the special theory of relativity and is consistent with it. However, it takes up Kaluza's hypothesis of an additional dimension and, by providing a simplified explanation for certain findings in theoretical physics, offers evidence for the reality of this additional dimension. These findings include the constancy of mass, the energy-momentum invariance, and the validity of Newton's second law even for four-dimensional accelerations. Finally, from the representation of a body's total energy as a function of its five-dimensional velocity, one can very easily derive a model of the universe in which four-dimensional space, along with the entire universe, travels through time at the speed of light. This yields explanations for mass and time, and the so-called relativistic mass increase turns out to be an increase in the kinetic energy of the five-dimensional velocity. In this interpretation of the relativistic mass increase, the fifth dimension proves to be indirectly perceptible, and one of its quantities, kinetic energy, proves to be measurable. This fulfills the requirement that in physics only what is measurable is recognized as existing. What has not yet been explained is the limitation of all speeds of action to the speed of light. However, an explanation is likely possible within this model of the universe. It is hoped that phenomena from other areas of physics can also be explained by this model, such as the orbitals of atoms as standing three-dimensional waves in four-dimensional space, the entanglement of quanta in the fourth dimension, or the redshift of galactic light caused by the curvature of the universe in the fourth dimension.